Hello everyone. The title of this video is Graphing Piecewise-Defined Functions. Now each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I am in their Algebra and Trigonometry text, section 3.2, Domain and Range, and I'm under the heading Graphing Piecewise-Defined Functions. And each example will either be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so I have these written out on paper. And yeah, all we're asked to do is graph the following piecewise function. Now, a piecewise defined function is no different than any other function, right? You have inputs and outputs, and for each input, you should get only one output, right? That is the definition of a function. But the thing that's different about piecewise defined functions is that it's defined by multiple rules. The way you calculate the output changes depending on what the input is. Alright, so you have to really pay attention to where the input is coming from in order to know how to calculate the output. So for instance here, right, here's a piecewise defined function, and usually there will be this, these brace symbols, braces, for piecewise defined functions. So you have y equals or f of x equals, and I got this function called f. Input is x, and remember f of x represents the output, and over on the other side is how the output is calculated. Now you see here the output is calculated in one of three ways, right? Now you don't do all three, because that would be three different outputs for an input. That's not a function. You're going to just one of these possible outputs, one of these rules. It all depends on the input though. So you do x cubed if x is a number less than -1. Alright, so for instance, just some examples here before I actually get into graphing this. If I said I'll evaluate some outputs here. Yeah, if I said what's f of, and I pick a value of x less than -1, right? Say -2. Right? Well, since this is less than -1, right? Since this is less than -1, the way I calculate the output is this top rule, right? And I ignore the other two, because -2 is not between -1 and 4. -2 is not greater than 4, right? It doesn't meet these conditions. So you just gotta really pay attention, right? Well, since -2 is less than 1, I'm going to calculate the output using this top rule and take -2 cubed. And that would be -8, right? And then what this tells me, is that the ordered pair, -2, comma, -8, is a point on the graph, right? Because we are asked to, graph this function here. When we graph this on the xy plane, input -2, output -8. F of negative 1.1 or something, right? Doesn't matter, right? As long as it's less than -1, right? Again, negative 1.1 is less than negative 1. You're going to this top piece, this top rule. So the output would be calculated as, negative 1.1 cubed. Right? So that'd be negative 1.331. Right? And then again, if you were talking about points on the graph, negative 1.1 input, negative 1.331 output would be a point on the graph. Right? Is a point on the graph of this function f. Okay? I know those are just some examples where I picked an input less than negative 1. Well, there are these two other pieces, right? So again, f of x equals, just negative 2. The output is negative 2 if the input, if x is between negative 1 and 4. So again, you got you got to pay attention to the conditions. So let me pick. So what I'm going to do here is I'm going to pick a value of x. I'm going to pick an input that satisfies this second condition that's between negative 1 and 4. So how about 0? This is between negative 1 and 4. Satisfies that second condition. So according to this rule, the way it's written, when the input 0, the output is going to be negative 2. Right? And again, the way something that would tell me about the graph is that the point 0, negative 2 is on the graph. I'll just say on graph. Right? And let me just do one more of these. Just pick an input, some value of x between negative 1 and 4, say 1. Right? That's also an input between negative 1 and 4, satisfies this middle condition. And if our input is in between negative 1 and 4, the output, f of x, is equal to negative 2. And then once again, this tells me a point on the graph. That means, input 1, output negative 2 is on the graph. And, I could do this all day long, right? There are infinitely many numbers between negative 1 and 4. But no matter what you pick, the output is negative 2. And then just a couple more of these, because I've done a couple from the first condition, the first line. Did a couple from the second line. Again, you can do more if you want. Let's just do a couple more here from this third line. Right, the third way to calculate outputs. F of x is the square root of x, right? The principal square root of x. If, right, x is greater than 4. So let me pick some values greater than 4. Right? Well, what's f of 9? Let's pick one that has a nice square root. 9 is greater than 4. It satisfies this third condition. Okay. And since it satisfies the third condition, right, it's greater than 4, then the way I would calculate the output is this bottom line, this bottom rule, the square root of 9. Right, and again, it's the principal non-negative square root of 9, so that's 3. And once again, this line here just tells me a point on the graph, input 9, output 3, right? So this point would be on the graph of function f. And again, you can plug in 5 for the square root of 5. It's just, no, that's not a nice number. It's 2 point something. Plug in 6, plug in 4.2, whatever, 2 times pi. Right? Lots of stuff. So let's do one more nice one here. If I plugged in 16, right? So again, this input, the input is greater than 4. It satisfies this third condition. So this would be the square root of 16, the principal square root of 16, which is 4. And once again, I'm told I can determine a point on the graph, right? 16 input, 4 output, right? This point would be on the graph of this function. All right, now, some of the tricky ones. What about, the numbers that are showing up in these conditions? -1 and +4. What about those? What would be f of -1? Well, let's see. -1. Is -1 less than -1? No. It's equal to -1. Is -1 between -1 and 4? No, it isn't. It's equal to -1. It's not greater than -1. And is -1 greater than 4? Absolutely not. So this input, -1, right, this doesn't satisfy any of the conditions, right? These conditions over here after the word if. This doesn't satisfy any of the conditions. So that means that there is no output when the input is -1. This is undefined. Undefined. There is no value. Right? There is no value. Okay. Now I will be using -1 when I go graph this thing, but what we're going to see is that there are going to be no points on the graph with an x value of -1. Same thing goes for f of 4. Right? Is 4 less than -1? No. Is 4 between -1 and 4? Well, no. 4 is equal to 4, not less than 4. Right? And is 4 greater than 4? No, it's equal to 4. Now, if I had greater than or equal to there, it would be, satisfying that third piece. But again, my input of 4 doesn't satisfy any of the conditions. So once again, there is not going to be a point on this graph with an x value of 4, right? There is no output when the x value is 4. And so once again, this is undefined. All right, so when making the graph of a piecewise defined function, I would recommend just graphing, one line at a time, one rule at a time. So let's actually graph this thing. All right. So I'm going to make a rough sketch, and then I'll show you on some calculators how you can make a better looking picture. I'm just going to do a rough sketch here. All right, so here's the XY plane, and then what I like to do is notice all the numbers that show up in the conditions. There's -1 and 4. I'll mark those off. So say here's -1 on the x-axis, right? These are values of x that are being mentioned. And then 1, 2, 3, 4, right? -1 and 4. And imagine that these form little walls. X equals -1 and x equals 4. To the left of -1, right, when x is less than -1, we're going to get a piece of the graph of this cubic function, right, y equals x cubed. And I'm hoping, based on previous videos on toolkit functions, library of functions, basic functions, that you know what the cubic function looks like, and constants and identity and squares and reciprocals and square roots and cube roots and absolute value, right? All those basic toolkit functions. All right. So now, again, let's just go one piece at a time. All right. So I'm going to start with this top piece. Y equals x cubed, but only if x is less than -1. So I did this earlier. I plugged in -2, and we got -8. So -8 on the y. Again, this isn't going to be beautiful, right? And I plot this point. -2, -8 is on there. All right, another one we plotted was -1.1, -1.1, -1.331 or whatever. But again, it's all going to be, -3, -27, -4, -64. It's going to be a part of the cubic function, which again, I'm assuming you know what that looks like. But it's not the entire cubic function, right? It's only a part of it. It's only going up to -1. All right, so here's where it might get a little tricky. What is -1 cubed? -1 cubed is -1. So I know it's not there, right? I know -1 is not less than -1. I know this doesn't contain -1, but if it were, the output would be -1. So input -1, output -1. But here's the tricky part, right? I'm going to put a hole there. See, I'm putting an open point at -1, -1. That is not there, right? But that's just where this piece will stop, right? And the rest of it is, again, part of the cubic function. Right? So something like this. Right? So yeah, -2, -8, -3, -27 would be on this, -4, -64, and so on. So it's just this part of the cubic function going down forever and left forever, but stopping at this hole, this missing empty point, right, at -1 when the input, if the input were -1, if it could be, the output would be -1, and again, but it can't be. The input can't be -1. That's why I've got a hole there. I hope that's clear. I hope that makes sense. Okay, now the next piece. This is for when x is between -1 and 4. So on the x-axis, this piece of the graph is just going to be from here to here, from -1 to 4 only, right, in between. Now we're seeing for this piece is just y equals -2. It's a constant function. Right? The output's always -2. So plotting some points, we plugged in, we got 0, -2. There's a point. We got 1, -2. Right, there's a point. 2, -2. 3, -2. Pi, -2, right? Every single value of x between -1 and 4 will give me an output of -2, right? It's basically just, again, just a piece of a horizontal line, but only a piece of it. Now here's where more of these holes are coming in, these open points. See at the left end, now I know -1 isn't part of this. -1 doesn't satisfy this, but if you were to plug in -1, the output would be -2, so I have a hole there. There's a hole, another empty point right below the previous one I drew at -1, -2. And then the same thing would happen at 4, right? I know 4 doesn't satisfy this condition, but if you were to plug in 4, you'd get -2 in this piece. So 4, -2, but again, because you can't plug in 4, right? 4 is not part of that domain, I'm putting a hole there. All right, and then the rest of it, right, for any value in between, we're getting an output of -2, right? So we get this piece of a horizontal line, but just between -1 and 4 on the x-axis. With these open points at the ends. All right, so there's a bit of a jump, right? So the graph from left to right going up, 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 up. You get to that hole, you jump down, you're at this other hole, and then you're on the graph again, right in here. And then you reach the end of that piece at that hole, 4, -2. And then finally we get to this last piece, where y equals the square root of x when x is greater than 4. So 5, 6, 7, 8, 9. When I plugged in 9 earlier, got an output of 3. Right, square root of 9 was 3. So here's a point that's actually on the graph, right, filled in, 9, 3. You go out to 16, you'll get an output of 4. Now, just like the earlier two pieces, right? Just like the top two pieces, I know 4 can't be plugged in, right? 4 does not satisfy this condition. But if it were, right? If it were, the square root of 4 is 2. So input 4, if it could be plugged in, if I plugged in 4, the output would be 2, but you can't plug it in. So I'm gonna have a hole here. Open point again. An open point, a missing point. That is not there. There should be no point with an x value of 4 on this graph. And then the rest of it is part of the square root function. Right? Remember how the square root function starts at the origin and goes up like a half a parabola opening to the right? But it's only the parts starting at this hole. Right? Going out to 9, 3, and then 16, 4, and so on. Right? Going up and right forever. But only starting at this hole at the point 4, 2. And there's the graph of this piecewise defined function. So you're on the first piece, then you make a jump, you're on the second piece, you make another jump, and then you're on that third piece. Now, let me show you how to graph this on a couple pieces of technology. Right, maybe get a cleaner looking picture. So here is a free online graphing calculator. Desmos, desmos.com. I know I've shown this to you in previous videos. Alright, so here's how you need to graph a piecewise defined function. And I said it earlier, when doing it by hand, we're just drawing one piece at a time. And I'm going to do the same here. Alright, we're going to do the same here. Now instead of f of x, I'm just going to put y. So for that first piece, right, the top piece was y equals x cubed. Now right now you see I have the entire cubic function. I don't want the entire cubic function, right? I only want the part of it where x is less than -1, right? That was the condition on the top piece. So after the function, after I put y equals x cubed, I put a brace. And then inside that brace you put the condition, x is less than -1, and then close the brace, and you see that? It cuts down, it's not the entire cubic function anymore. It's just the part of the cubic function that has x values, has inputs less than -1. And you see when I move my points around here, right, there's -1.61, blah, blah, blah. And look at the top though. See that hole? See how that is a hole, -1 comma undefined? That's exactly what I had in my drawing. Right? There is no point there. There should be no point with an x coordinate at -1. But you notice how this is at where -1 comma -1 would be? Because if you were to cube -1, you'd get an output of -1. But again, you can't plug in -1, so that's why it's an open point instead of a closed point. Okay, and again, if you're not clicking on it, though, it's hard to tell. Right? They kind of make it look like it's there. All right, then the second piece. Again, y equals -2. Now you see it's the entire line right now, but I don't want the entire line. Right? I want just the part of the line where x is between -1 and 4. So again, I put the braces and I put -1 is less than x is less than 4. And there it is, right there. That was on my graph. Now maybe I should make it the same color, right, because they are part of the same picture. Right. And again, you click on any of these, right? You see the x coordinates between -1 and 4, and the y coordinates always -2. And look at the left end. You see it doesn't look like there's a hole there, but there is a hole there. -1 comma undefined. And that hole is at the place where -1 comma -2 would be. It's just -1 can't be plugged in here, so that's why there's a hole there and not a filled in point. Same thing at the other end, right? 4 isn't satisfying the condition. 4 can't be plugged in, but if you were, you'd get 4 -2, and they put a hole there, an empty point, 4 comma undefined, right? Exactly like I have in my drawing. All right, and then the final piece, again, third slot here, y equals the square root of x. Now, if you just leave it like this, it's graphing the whole thing. And if you leave it like this is not a function anymore, right? This does not pass the vertical line test. right? A graph should pass, if a graph is a graph of a function, it should pass the vertical line test, right? No vertical line should hit it more than once. And if I leave it like this, you're going to have a vertical line hitting this thing more than once. So it's got to be cut. And that's why right after this, I put the condition, right, in braces that x has to be greater than 4, right? We only want to look at the piece of this where x is greater than 4, not equal to 4. So notice again the hole at 4. Right, there's 4 undefined, another hole. 4, the square root of 4 is 2, so it's at the point 4, 2, but it is not there. Right? And then everything after that has an x value greater than 4, and then the y value is just the square root of the x value. And again, I should probably make that the same color, just because they're the same graph. Right? And again, this is it. This is your piecewise defined function. Right? And it passes the vertical line test. Right? Again, I know it doesn't look like it, but there are no points at -1. So that vertical line doesn't actually hit the graph. And there are no points at x equals 4. So that vertical line, even though it looks like it's hitting the graph twice, is not, right? Those points aren't really there. 4 undefined, 4 undefined. Right? Okay. Great. All right, so that's one way you can make a piecewise defined function on this Desmos site. Another way you can make it, I've got a TI-84 emulator. So let me show you. I'll pull that up. All right. And I'm going to put up, now this is a little more involved, I feel, but still doable. So you go to your y equals menu. Let me get rid of that. That was an old video. Go hit y equals, and then you put in the rule for the first piece, right? It was x cubed, right? The first piece of the piecewise function, x cubed. And then you're going to multiply this by the condition, all right? Now the condition is, no, not list, I want to go to test. Yeah. So if you hit the second button and then the math button, there's a test menu above it. And you see all these inequality symbols here, and then you go to the logic, there's and or and stuff like that. Let's see, conditions. Oh, okay, so you go to conditions. This will be a lot faster. Go over to conditions, and the first condition, right, was x needed to be less than -1. Right, and put that in parentheses. Right. And let me show you what happened. Let me show you this right now. Right. These conditions, when they're true, they have a value of 1. And when they're false, they have a value of 0. All right, so it's like it makes the rest of it disappear. So let me show you what happens right now when I hit graph. All right. See? You have that piece of x cubed that goes up to -1, but then after that, you have a value of 0. So, it's not as nice as Desmos, where because I mean, there's not a hole here. There's actually the point -1, 0. So it's not as good, I'll say, as drawing one piece at a time in Desmos. But anyway, let's go back. Go back to the y equals. So I have the first piece rule times its condition. Then you add, right, plus. Then the second piece rule, right, which is -2. Right, the output was -2 the way for that second piece, times its condition. Right, so I'm going to go second test over to conditions. Now this needs to involve an and. All right, an and, because we have x is between -1 and 4 for the second piece. So that's x is greater than -1 and x is less than 4. Right, so that'll be this sixth condition here. All right, and I need to scroll back and put in Insert -1. I probably should have just put -1 first. Oops, that replaced the parentheses. I don't want that. I want it here. Insert negative, insert 1. Oops, what did I do? Goodness. Insert. Alright, you know what? Let me just. Alright, I'm gonna. Alright. Let me go back. Actually, let me do this instead. Delete all this. Alright, so I put -1 first, and then that condition. That's a lot easier than replacing stuff. So, see, I like doing the Desmos more, as you can probably tell. So there, -1 less than x, and x is less than 4 at the same time. Close the parentheses, right? So now when I graph, you'll see the first two pieces drawn. Right, there's x cubed, and then there, up to -1, and then there's y equals -2 up to when x is 4, and then the rest of the time it's 0. Again, unfortunately there's no holes here. Right. And then back to the y equals menu. Then we're going to add, so first piece times its condition plus second piece, second rule times its condition, and then plus, and then the third piece, which was the square root of x, times its condition, in parentheses, right, test conditions, and it was x is greater than 4. And then graph, right? And you'll see the same picture I drew by hand, the same picture we had up in Desmos. Where's the x cubed part? I hate this. I don't know why. I don't know why that's not showing up. Well, it should be good in a table. Yeah, stick to Desmos. But yeah, I see in a table. I plug in a number less than -1, say -3. That'll give me -27. Error. Why is there an error? Let's see. X cubed times its condition plus -2 times its condition plus the square root of. I see what happened, because you can't take square roots of negatives, and it's putting it there. Well, gee. I guess I should just graph that separately then. Sorry about this. You can probably tell I'm much more comfortable with Desmos. So if I do y2, go to y2, I guess you could graph each part separately as well. It's just annoying. Yeah, y2 equals the square root of x times its condition. And then x is greater than 4. And then graph that. You'll see there's the first two pieces, and then there's, see, it's got the annoying 0 parts to it, but got the x cubed up to -1, you got the y equals -2 between -1 and 4, and then you got the square root of x up here after x equals 4. Yeah, that's annoying. That is annoying. So I would actually just say, forget all that. What a waste of time. I apologize. And stick to Desmos. A lot easier. Right, just graphing one piece at a time with these braces, and you can see very nicely the piecewise-defined function. Alright, great. Alright, so I'll come back to this. Let's go back to our paper and get to the next example. So, long one there, that was half an hour, but hopefully after the next few, it'll be a little easier. All right, so the next one's not got, it doesn't have 3 pieces, it's got just 2 pieces, and I think most of the rest of the examples have just 2 pieces. So here, f of x equals, x plus 1 is how you calculate the output, but only if x is less than negative 2. All right, and f of x is negative 2x minus 3, but only if x is greater than or equal to, this one actually includes negative 2. All right. If it was just greater than negative 2, then then there wouldn't be negative 2 as an x-coordinate for any point at all. All right, so this one I'll just start doing by hand. Now these, you should recognize these as linear functions, right? mx plus b here. So I'll make graphing this a bit easier. Now in the conditions, right, the only number that's mentioned is negative 2. Right, so I'll put negative 2 down. And for this first piece, I'm just plugging in values of x less than negative 2, right? So, if x were negative 3, negative 3 plus 1 is negative 2, right? f of negative 3 would be negative 2. And I'll actually fill that in, right? Negative 3 actually belongs to the domain of that first piece. Now, I know it's a line, so you only need 2 points. So what about negative 4? Right? Negative 4, plug in negative 4, say. F of negative 4 is negative 3. And I'll plot that point, negative 4, negative 3. And the rest of it should be the rest of this line, right? Up until you hit x equals negative 2. Right? So just that piece of the line. Now, when you plug in negative 2, right? Negative 2 plus 1, if you were to plug in negative 2 to the top piece, negative 2 plus 1 is negative 1, but there's going to be a hole. Right? Don't forget, there's going to be an empty point. So negative 2, negative 1, empty point, and that's where the graph of this line is going to stop, at that empty point. All right. All right, and I'm done with the first piece, and I move on to the next piece. Now here, I can plug in anything greater than negative 2 or negative 2 itself. So why not start at negative 2? Why not, If I plug, now negative 2 times negative 2 is 4, minus 3 is 1. So f of negative 2 is 1. Right, so this will actually be a filled in, a solid point, right? Because negative 2 can actually be plugged in here. So negative 2, 1, solid. And that's where this piece will start. It starts at negative 2, and then we go to the right. And then an easy one would be f of 0. Right? 0 is greater than negative 2, and f of 0 would be negative 3. So I got 0, negative 3. And I know this is a linear function, so those are the only 2 points I really need. And starting from the point negative 2, 1, going down, I draw a line that passes through the point 0, negative 3, and there's the, and then it's going down forever for all values of x greater than negative 2. And there you go, that's it. All right. Piece 1, piece 2. It passes the vertical line test. All right, and again, I know you're probably thinking, no, it doesn't. What about, again, at x equals negative 2, if you draw this vertical line in, it's hitting the graph once. This hole is not really there. Right, so it's only hitting the graph once. Right, this does pass the vertical line test. It is still a function. Every input gives you one output. Right. And again, let's go to Desmos and show this. Right. I like doing that with graphs, especially my hand drawings aren't always the best. So we got multiple pieces here, right? 2 pieces. So again, I'll just do y equals instead of f of x equals. Y equals, now the first piece had the rule x plus 1. And again, they give me the whole line here, but I don't want the whole line. I just want the piece of it, right? So I put braces, the piece of it where x is less than negative 2. And there's that first piece, right? Now notice, right? Notice again the hole here at negative 2, negative 2. All right, there's negative 2 comma undefined. It's not there. Right? But then the rest of the ones are solid. Right? The rest of the points are solid because they actually belong. Right? Then the second piece, y equals negative 2x minus 3. But again, I don't want that. If I leave that entire line there, it's not a function anymore. Right? It doesn't pass the vertical line test. So I only want the piece of it where x is greater than or equal to negative 2. Right? And again, I'll make them the same color. They're part of the same function, same graph. And now you see it. There is negative 2, 1. That's a solid point at the end there because it was x is greater than or equal to negative 2. Negative 2 actually belonged to the domain of this second piece. And then all these other points are solid here. And then there's 0, negative 3 that I also plotted by hand and going down forever. Right. So great. There's the graph of that piecewise defined function. Right. Just a couple pieces, not so bad. All right. And I'm doing that for the rest of these. Right. Doing that for the rest of these. I'm hoping simple stuff. All right. I'm hoping that after seeing a bunch of these, practicing some on your own, it'll be easy enough. All right, example 3, same deal, y equals f of x equals, and then you got the two pieces once more. It's just x plus 1 if x is less than 0. It's x minus 1 if x is greater than 0. So notice here, f of 0 will be undefined. There will be no point with an x value of 0. All right. All the points on this first piece I'm drawing are going to have an x value less than 0. And all the values, all the outputs, all the points on the next piece are going to have values of x greater than 0. No value of x equal to 0. Right. All right, so once again, a rough sketch by hand first. Now these are both linear functions again, so I know that this should be an easier graph to make. Here's 0 on the x-axis, right? That's where in line with the y-axis here. And then if I go, for the first piece, I plug in values of x less than 0, so say negative 1. F of negative 1 would be negative 1 plus 1 would be 0. So I got negative 1, 0. Now, 0 plus 1, if you were to plug 0 in, that would be 1, and there would be a hole. Right? Because again, 0 is not actually part of the domain of this first piece. So you would have 0, 1 as a hole. Right? And then the rest of that piece would be to the left of that hole. Right? There's the rest of the line. There's y equals x plus 1, but stopping at this hole. Right? Stopping at the point 0, 1. That's not actually there. Right? Okay. And then for the second piece, plugging in values of x greater than 0, so how about positive 1? Now if I plug in positive 1, right, f of 1 would be 1 minus 1, that'd be 0. Nice. So I got 1, 0. And, if you were to plug in 0, you'd have 0 minus 1, which is negative 1, and again, there would be a missing point there, a hole, an empty point. So 0, negative 1, but a hole there, right? An open point. Please don't fill that in. That's not actually there. Right? But then the rest of the friggin' second piece, right, would be, sorry about the friggin', right? The rest of the second piece would be this line here, right? It should be parallel to this first part, because they're both lines, linear functions with a slope of 1. And there you go. There's the piece of the line y equals x minus 1, but where all the x coordinates are greater than 0. And that's it. Again, pretty simple when they're linear functions, I think. And again, let's take a look. Let's go to the Desmos site. I'll put these pieces in one at a time. So the top piece was y equals x plus 1. But again, I don't want the entire graph. I just want the piece of it where x is less than 0. Right? And once again, you're going to see now. I know there's this gray point there. When you go over the gray point, it says 0, 1 because it's just highlighting that gray point. But if you actually click on the graph and move around, it's going to say 0 undefined. See that hole there? It's not there. Right? Unfortunately, they do have the gray part. Now, if I click off this, it's gone. Right? If you click on it, it comes back. But yeah, this should not have a point with an x value of 0. And as you can see, when I click on it, it doesn't. Right? Okay. And then the second piece, y equals x minus 1. Again, not the whole line, right? If I left it that way, it wouldn't be a function anymore, right? It wouldn't pass the vertical line test. I want the piece of it that's just got x values greater than 0. And there you go. And that's exactly what my drawing looked like. Again, I'll make them the same color. All right, and another hole. See 0 undefined at the very end here. Right? It shouldn't be there because this is only, the points on this piece of the graph should only have x coordinates greater than 0, not equal to 0. All right, wonderful. Now again, you can't tell until you actually click on it. Great. All right, next example. All right, so now one piece is a quadratic, right? That basic square function, y equals x squared, which again, you should know what those look like, parabolas, right? But it's only a piece of it. All right, it's f of x equals x squared if x is less than 0. All right, if x is less than 0. And f of x equals 1 minus x, a linear function, part of a line, but only the part where x coordinates are greater than 0. So notice once again, x is less than 0, x is greater than 0. There is no x equals 0. So f of 0 is once again undefined here. There is no point with an x coordinate of 0. Okay. So again, the rough xy plane by hand. Here's 0 on the x-axis. Now, the first piece, right, I'm plugging in values of x less than 0. So like negative 1. Now, f of negative 1 would be negative 1 squared, which would be positive 1. Right? And then, plug in, say, negative 2. Right? F of negative 2 would be negative 2 squared, which would be positive 4. Right? And it's part of a parabola, right? Basically just the left half of a parabola. And then, if you were to plug in 0, right? 0 squared would be 0, and but you'd have a hole there, right? An empty point at 0, 0. So an open point here at the origin, 0, 0. But then the rest of it, right, to the left of 0, where x is less than 0, is this part of this parabola. Right? And it's not as easy as a line here, right? Something like that. But just up until the point 0, 0, where there's a missing point. Right? Because again, x can't be equal to 0 for that first picture, that first piece. All right, then next piece, plugging in values of x greater than 0. So like 1. Now f of 1 would be 1 minus 1, which is a 0. Right, so there's 1, 0 filled in. That's actually a point on the graph. And then if you were to put 0 in, I know you can't, but if you were, right, you'd have 1 minus 0, which is 1, and there should be a hole. Right? It should be an empty point at 0, 1. Right? 0, 1. So open point here at 0, 1. Right? It's not actually there, and then the rest of it's a line. Right? It's a linear function, 1 minus x. The rest of it's part of the graph of y equals 1 minus x, right, for where all the x coordinates are greater than 0. And that's it, right? Just the two pieces. And let's take a better look at it again on Desmos. All right, so that first piece, right, y equals x squared. But again, not the entire parabola. I just want the part of it where x is less than 0. And there it is, that left half. So again, you move your cursor around this and you'll notice it looks like the origin's on it, but it's not. So look, 0 undefined. There is a hole there at 0, 0. And the other piece was y equals 1 minus x. Again, don't leave the entire graph up. Don't draw the whole thing, because that's not a function. Right? It doesn't pass the vertical line test. I just want the part of it where x is greater than 0. And there it is. Now notice, when you actually move the points, move around, you see all these solid points, where the x coordinates are greater than 0 here. But see, at 0, a hole, an empty point again, 0, comma, undefined. Right. So there should be no points on this graph with an x coordinate of 0. Right. And it looks pretty much like my hand drawing. Wonderful. Okay, next one. Right, this is the last one I'm going to be drawing, and then the examples after this, just pretty simple evaluations. I mean, I've already been evaluating these, so hopefully you got the hang of that by now. So y equals f of x equals, x plus 1 if x is less than 1. Notice just less than 1 though, so there's going to be a hole, a missing point when x equals 1. Right? And then the second piece is y equals x cubed, right? Part of a cubic function, but only if x is greater than 1 or equal to 1. So at x equals 1 here, there will be a solid point. Right? There'll be an empty point at 1 for the first piece, and a solid point at 1, a filled-in point at 1 for the second piece, because it actually belongs to the domain x equals 1 of that second piece. All right. Okay, so again, the xy plane. And the numbers mentioned in the conditions here, the only one that is the number 1. All right, now I'm going to look at this first piece. Start plugging in values less than 1. So how about 0? Now f of 0 is simply going to be 0 plus 1, right? So 1. So 0, 1 is a point on this graph. It's solid, right? And then if you were to plug 1 in, again, there's going to be a hole though, a missing point. If you were to plug 1 in, right, 1 plus 1 is 2, and you're going to have a hole at that point. 1, 2. So here's 1, 2, 1, 2, but open point, empty point, missing point. And then the rest of it's a line, right? Y equals x plus 1 is a linear function, so the rest of it's a line starting, if I go from right to left, that'll be from the open point to the left there. So there's a picture of that line, but only where x coordinates are less than 1. All right, now for the second piece. I can actually plug in 1. So let's do it. What's f of 1? Well, that would be 1 cubed, which is 1. And this will be solid. 1, 1, solid. It actually belongs. X equals 1 is actually part of the domain of this second piece. And then say I plug in 2, right, 3, 4, anything greater than 1. Right? Now f of 2 would be 8, right? 2 cubed. So sorry about this. 4, 5, 6, 7, 8. Let's just say 8's up here. Sorry. And you got 2, 8, solid, right? That actually belongs to the graph. And the rest of this graph is part of the cubic function. Remember, the cubic function looks like this. But I don't have this first part of it. It's starting here at the point 1, 1. Right? It's got to be starting here at the point 1, 1 and then shooting up very quickly. And there's the graph, a very, very rough sketch of the graph of that piecewise defined function. Again, let's take a look at it in Desmos. All right, so once again, first piece, y equals x plus 1, but not the entire thing, right? Just a piece of it, where x is less than 1, right? And again, there should be, because x is strictly less than 1, right, there should be an empty point when x equals 1, right? And you see that there, 1 comma undefined for this first piece, right? It's undefined for this first piece, but not for the second piece, right? The second piece actually is going to have a point when x equals 1, y equals x cubed. And again, not the whole thing, because if you leave it like this, it's not a function anymore, right? Only when x is greater than or equal to 1. Right? There. And now it's a function, and there should be, see, it's a solid point 1, 1. when x equals 1, there's actually a point there. It's not undefined. And then the rest of them, is whatever the x is, the y value is x cubed. And then again, you probably change the color so that they're the same color, but whatever. Right. And that looks pretty similar to what I drew by hand. Excellent. Okay. All right, so now, you know what? I'll graph these as well. Right, might as well. Now for the next couple exercises, I'm just asked to evaluate what's f of negative 3, what's f of negative 2, what's f of negative 1, and what's f of 0 for the next couple exercises. So 6, you got f of x equals 1 if x is less than or equal to negative 3, and 0 if x is greater than negative 3. That's a real easy one to draw. So here's, negative 3 on the x-axis. And then your outputs are 0 and 1. Right? So, the output's 1 whenever x is less than or equal to negative 3. So you're going to have negative 3, 1 is a solid point, right? Negative 3 actually is in the domain there. And then for all the x values less than negative 3, the value is 1. So you get part of a horizontal line. And then when x is greater than negative 3, you get an output of 0, but not negative 3 itself. So there will be a hole, an open point at negative 3. So negative 3, 0, and then everything else, output is 0. Horizontal line. There's the graph of that. That was a quick one. All right, so all these values here, f of negative 3, right, just again pay attention to the input. Negative 3, which condition does it satisfy? Negative 3 is not greater than negative 3, it's less than or equal to negative 3. So the output's 1. All right, so there's part 1. Then what's f of negative 2? Right. Negative 2 is not less than or equal to negative 3, it's greater than negative 3. Right? Negative 2 would be here. Right? So the output's 0. Same thing for the other two. F of negative 1 would be 0, because negative 1 is greater than negative 3, right? And f of 0 would also be 0. You're seeing that on my graph here. Right? F of 0 would be 0 as well. Right? And just pay attention to the input so and say which condition does that meet, so you know how to calculate, how to find the output. All right, so that one's pretty simple. 7, same thing. I'm asked to do f of negative 3, negative 2, negative 1, and 0. All right, so let's just do that, and then I'll make the drawing in Desmos and we can verify our results. All right, so f of negative 3. So which condition does that satisfy? Is negative 3 less than or equal to negative 1? Yeah. So I go into this first piece. It'd be negative 2 times, the input squared times negative 3 squared plus 3. Negative 3 squared is 9, times negative 2 is negative 18, plus 3 would be negative 15. All right, so there's f of negative 3. And again, what that tells me about the graph is that the point negative 3 comma negative 15 would be on the graph. And we'll see that when I go to Desmos in a second. Right. F of negative 2. So negative 2 is still less than negative 1, so I'm in this first piece again. So negative 2 times negative 2 squared plus 3. That's negative 2 times 4, negative 8, plus 3, negative 5. Sorry. So the point negative 2, negative 5 will be on the graph. Right? F of negative 1. Negative 1 is still less than or equal to negative 1, right? This first piece, because of the equal part, is satisfied. So I'm still in the first piece. Negative 2 times negative 1 squared plus 3. Oh, that's negative 2 plus 3, that's 1. Right? So the point negative 1 comma 1 should be on the graph. And then finally f of 0. Well, now, 0 is not less than or equal to negative 1. So I'm not doing the first piece, right? 0 is greater than negative 1. So I'm doing the second piece, which is 5 times the input, 5 times x, minus 7. So we get negative 7. 0 input, negative 7 output. And let's check this. Right, I guess I should have circled these, right? These were what they were asking for there. But let's check this, right? So I'm going to graph this on Desmos, and I'll put in these points and see that they actually are on the graph. Right. All right, so first piece, right? Y equals, it was negative 2x squared plus 3, but not the entire thing, right? Just the part of it where x was less than or equal to negative 1. Okay, and then the second piece, y equals 5x minus 7, but not the whole thing, right? It won't be a function if you leave it the way it is. But only the part where x is greater than negative 1. Right? And I'll make that the same color. Why not? Right? It's the same graph. Right. Here it is, right? There's the graph of your piecewise function. Now there should be a hole when x is negative 1 on this piece, right? But not on this piece, right? There's not a hole there. Negative 1, 1, which we said would be on it. Now let's just see these other points, right? We said that negative 3, negative 15 would be on this thing, and there it is. You see it's definitely on the graph. The next one was negative 2, negative 5, right? We're seeing that's on the graph there, that red point that just popped up clearly on the green graph. We just saw negative 1, 1, so I'm not going to put that. And then 0, negative 7, right, is right there, also on the green graph, right? Very clear. So we did a good job. Right? Always check your work, of course. All right. And then the last couple examples are very similar, but instead of finding f of negative 3, negative 2, negative 1, and 0, they just change it up on us. Right, so in example 8, we've got a f of x equals x squared minus 2 if x is less than 2, or it's 4 plus the absolute value of x minus 5 if x is greater than or equal to 2. And we're asked to evaluate f of negative 1, 0, 2, and 4. Right. So f of negative 1, again, just pay attention to the input. Which condition does it satisfy? Is negative 1 less than 2? Yes. So I'm going to this first one. So that'd be negative 1 squared minus 2. That's 1 minus 2. That's negative 1. Right, and that's all they wanted. But that means that the point negative 1 would be on the graph. Right, again, we'll verify this in Desmos. Then f of 0. Again, which condition does this satisfy? Is 0 less than 2? Absolutely. So I'm going to the first piece again. It would be 0 squared minus 2, which would be negative 2. That's all they wanted, but if I point out a point on the graph, the 0, negative 2 would be on the graph. What's f of 2? Right, they want f of 2 next. Now, is 2 less than 2? No. It's equal to 2. So it's in this. I'm in the second piece, because this is where x is greater than or equal to 2. 2 is equal to 2. So I'm going here. Right? The output will be calculated 4 plus the absolute value of 2 minus 5. Now 2 minus 5 is negative 3, and the absolute value is positive 3. This is just 4 plus 3, that's 7. So the 0.27 should be on this graph. And then f of 4. Again, 4 is not less than 2. 4 is greater than 2, right? So we're satisfying this, our input satisfies this second condition. We're going to go to this second way to calculate the output. 4 plus the absolute value of, x minus 5. X is 4 here, 4 minus 5. All right, 4 minus 5 is negative 1. The absolute value of negative 1 is positive 1. So this is just 4 plus 1, that's 5. The output's 5. So input 4, output 5. Right, and then I'm going to just verify, by graphing in Desmos. Again, you can graph by hand if you want to. But I'll just verify in Desmos that these points are actually on this graph, that all these outputs are correct. All right, so first piece, y equals x squared minus 2, but not the whole thing, right? Just the part of it where x is less than 2. Right, and there should be an open point when x is 2, right? As you can see here, right? 2 undefined for that first piece. Second piece, y equals 4 plus the absolute value. Now you can just do ABS for absolute value in Desmos. Absolute value of x minus 5. But again, not the whole thing, just the part of it where x is greater than or equal to 2. And there you go. And now that should have a filled in point at 2, right? Because it's equal to 2 as well. See 2, 7. And we said that on my paper, right? I said 2, 7 would be on this, and it is. Right? You see that solid point there. All right, so let's plot the other 3. Let's see if we get the other 3. All right, so I said that -1, -1 would be on it. Oop, yeah. -1, -1. I put -1, 1. Yeah, there it is. See, it's on the green graph there. 0, -2. All right, 0, -2. Definitely on it. Look at that. And the other one was 4, 5. Right, 4, 5. And that's on the purple part, right, on the second piece. Excellent. Okay. All right. And then I have one more example. And it's back to, just like the first example, I'm back to an example with 3 parts. Right? There can be 2 pieces, 3 pieces, 5 pieces, right? It doesn't matter. Right? I'm just trying to stick to kind of simple things with 2 or 3 pieces. All right, again, I'm asked to evaluate f of -1, f of 0, f of 2, f of 4. All right. So what's f of -1? All right, so again, look at your input and say which condition is satisfied. Is -1 less than 0? Yes. So I'm going to this first piece. It says 5 times -1, which is -5, and that's it, right? And then again, if you want to say some more information, this line here would mean that the point -1, -5 is on the graph of this piecewise defined function. Then what's f of 0? Now, is 0 less than 0? No. Is 0 within 0 and 3 but equal to 0 as well? Yeah, it satisfies this equal to part, right? 0 is less than, it's less than or equal to 0, and 0 is less than or equal to 3. This second part's true. And for all these inputs in the second piece, the output is 3. All right, so the ordered pair 0, 3 should be on this graph. And then what's f of 2? Well, same piece. 2 is not less than 0, but 2 is between 0 and 3. So the output's 3 again. Easy. So the ordered pair 2, 3 should be on the graph. And finally, what's f of 4? Again, 4 is not less than 0. 4 doesn't fall within 0 to 3. 4 is greater than 3. That's true. The third condition. So I'm calculating it this way, doing 4 squared, right? X squared, which is 16. Right, so the ordered pair 4, 16 should be on this graph. And again, I should have circled these, the value, the outputs. That's what they wanted. And once again, I'm going to verify that these points are actually on this graph, the graphs of these pieces in Desmos. So the first piece, y equals 5x, but only the part of it where x is less than 0. All right, so there should be a hole, an empty point at 0, right? 0 is not actually part of that domain. You can see there's a hole at the origin, right, on that first piece. Second piece, y equals 3, but again, not the whole thing. I want the part of it where 0 is less than or equal to x, and x is less than or equal to 3. Right? Now this one, because of the equal to signs, there should be solid points at 0 and at 3, and you're seeing the solid point 0, 3, solid point 3, 3. Right? They're solid. They're not holes. They're not empty. Because 0 and 3 actually belong to the domain of this piece. And the final piece is y equals x squared. But again, not the entire thing, clearly not a function if you leave it that way, but only the part of it where x is greater than 3. Right? and that'll be up here because that was like 3, 9. Yeah. And you see that hole, right? There should, 3 is not actually part of the domain of this third piece, so there should be a hole at 3, and there is. See, 3 undefined. It's in the place where 3, 9 would be, right? Because 3 squared is 9, but again, 3 is not part of the domain, so empty point. I hope that's clear after all these examples. Okay, now let me just plot the points that we said there be, right? Well, we plugged in -1. There should be the point -1, -5. There it is. It's on that first piece. There should be the point 0.03, right? We saw that already, right? It's on the second piece there. There should be the point 2.3 on the second piece, right? You see it there. And there should be the point 4.16 on that third piece, and you see it there. And it looks good. Excellent. Excellent. All right, so that's it. All right, I know that was a lot, a little over an hour. That first example was the worst, right? It took the longest because I wanted to explain everything as much as I could. And I'm hoping watching those other examples helped as well, help clear things up. I think the trickiest part is knowing where there's going to be an empty point and a solid point at the ends of these pieces. So remember, if you have just less than or just greater than in your conditions, there's going to be a hole there, an empty point. And if you have less than or equal to, greater than or equal to, the equal to parts there, then there's going to be a solid point at those ends of the pieces. Right? And you've seen that throughout these examples. Now there is a way to graph on the TI-83, 84. These, that you saw, it's kind of annoying, especially if there's like roots involved, like you saw with that first example. So if I were you, and wanted to see what these things looked like without drawing by hand, I'd do Desmos and just graph each piece, y equals each piece separately, and make sure you put those braces in with the conditions. I think those give a much clearer picture, and they're easier to move around, easier to see. It's just my opinion. Do whatever you want. All right. Of course, you should also be able to graph these by hand, right? You saw me graph, I think, the first 5 examples by hand. You should be able to do that as well. Great. And I'm hoping that watching me go through these 9 examples here help you in some way, when you're asked to graph a piecewise defined function on your own. And thank you very much for watching.